I think it's time to start. So guys, first, any question from last time? Last time we finished the unilateral Laplace transform, which we showed that it's very useful for solving initial value problem. And today, as we said, we are going to go into a different chapter. So it's like a totally different topic, but actually very similar to Laplace transform. So we go into our last chapter, chapter 10, the Z transform. And this is basically the Laplace transform for the discrete time value function. So it's going to be very similar to Laplace transform, except at a few points. As you see, so we are going to introduce the Z transform, and there is going to be ROC, and we are going to say what is inverse transform, and it's going to be the pole zero plot analysis, etc., properties, and the unilateral transform. Okay, and so let's start with the Z transform. So as we say, it's basically we follow the continuous time case exactly. So we start with our motivation, saying that we know that for our discrete IoT system, it has an impulse response h, and and we know that the complex exponential z to the n are going to be the eigenvalue for every IoT system. So if your input is z to the n, your output is also z to the n, but times some eigenvalue h of z. And this h of z is we derived in chapter 3 is the summation h of n z to the minus n, and h of n is the impulse response. And just like in chapter 9, so when we do Fourier transform, we say those z are purely imaginary, right? So when we do Fourier transform, those z are e to the j omega. So z is not purely imaginary, but it's a complex exponential of purely imaginary exponent. Yeah, so that's when Fourier transform. But now we do like analytical continuation, so now we don't put restriction on z anymore. So z can now be any complex number, and there is going to be an ROC of this z, and but back and forth. So now z is anything, but so we look back to the Fourier transform. Fourier transform means that z is e to the some purely imaginary j omega. And if you think about this thing on the z plane, then that means that z is on a unit circle. And as we say, there is going to be ROC, and there is going to be pole zero plot. So that's a comparison of chapter 10 to chapter 5. But we can also do comparison of chapter 9. So remember, we deal a lot with those Laplace transform. So Laplace transform, we say is a big X over S, where this S is arbitrary complex number, and this is integral over X and times e to the minus st dt. So you compare this thing and this thing, you see that it's very similar. So the X is like this h of n. And you have the integral because x is continuous, and you have summation. And the most difference is that you are times e to the st, but now you have z to the minus n. Okay, so you compare this thing, you see that z is like e to the s. So you take an exponential on this s. And why do we do that? So let's go ahead of ourselves a little bit. So we have the comparison between Laplace transform and Z transform. So Laplace transform kind of feel like this. There is going to be pole somewhere on your S-plane, and you have some ROC like this. And you think about the real part of your S, we call sigma, and the imaginary part of your S, we call omega. And in Z transform, you are taking this exponential of S, right? So you are plotting against Z, which is like e to the S. So first of all, the reason why to want to do that is because remember now your x or your h is discrete time, and as we say, if you are discrete time, then always you have this 2 pi period in your omega. So this omega will have a 2 pi period, so doesn't make much sense to draw the whole imaginary omega. So although we haven't been doing that, but if we draw in z, then we can make things a little easier. So now this omega kind of wrap around, right? Because you take this exponential. So those e to the j omega is just so if you go omega, say that from 0 to 2 pi, that just means you go from the 0 angle to 2 pi angle, and so you are just going to take a circle in your z plane. And I guess for the reasons, and another reason is just the numbers in this z is better for discrete time, as we're going to see that. So remember that in Laplace transform we analyze a lot of the rational functions, and rational function can do partial fraction expansion, and you can see that the point 0 is very easy. And then it turns out that in discrete time, although you take this exponential, and a lot of functions, they are still going to give you rational function in the z plane, and you can do a lot of analysis. But okay, so back to the comparison between z transform and the Laplace transform. So you see that we take z to z as e to the s, and now if you think about z as the polar decomposition, so there is an r and an e to the j omega, and then you see that this r will depend on the real part of your s, right? So if you think about s is sigma plus j omega, and then this r will be e to the sigma. So when you take sigma to plus infinity, then your r is going to be plus infinity. So you go to plus infinity. And also if you take sigma to negative infinity, then r actually becomes 0. So negative infinity mapped to this original here. So that's quite interesting. And so the plus infinity and negative infinity are actually going to be two different points. Either it's going to be the 0 and infinity here. And once again, we think about z at infinity at some point, and you can have pole 0 there. And you can also, as we see here, you can also have pole 0 at z equal to 0. And then, as we said, if you go along this omega axis, so say this carded pole here is actually, so a straight line in this s plane is actually a circle in the z plane, and it's taking nicely about this periodic 2 pi. So yeah, the periodic 2 pi here corresponds to your periodic 2 pi in omega in s. Okay, and as we see, so this is a spoiler. So the ROC in the z plane is going to be those donut shapes. So you have strips in your s plane for Laplace transform, and you will have those rings in your z plane. Okay, and once again, they will be bound by the poles. Okay. Any question about the comparison? This is jumping ahead of ourselves a lot, so don't think too much about numbers, I guess. Okay, so let's go back to the derivation of z transform. I guess not quite derivation, but the definition of z transform. And as we said, the z transform is defined as, so just multiplied by what we have the eigenvalue equation in chapter 3. So we have big X of z defined by this summation x n from minus infinity to plus infinity, x of n times z to the minus n. Okay. And okay, so this is a function of z. So you change to different z, you get different big X of z. And z is any complex value, but you want it to be converging. Okay, and so some notation. So we write the z transform of some function as this z curly bracket of your function. Okay, so big Z curly bracket. And also there is going to be Z transform and inverse Z transform, and when you form a pair, just write this. So left right arrow with curly with the script big Z on top. Okay, so x of n and its Z transform is big X of Z. And once again, this is consistent of our notation in chapter 5. So remember in chapter 5 we write big X of e to the j omega. and now you see that this e to the j omega is just z. Okay, the e to the j omega is just some spatial value of z, and in particular on this picture you can see that so the e to the j omega is z on this unit circle, right? Because e to the j omega all has absolute value 1. So when we take a Fourier transform, we are just thinking about z on this unit circle, and it's like in Laplace transform we are taking the s on the imaginary line, because the imaginary line you take it exponentially map to this unit circle. Okay. Some geometric way to see the z transform. Anyway, let's see more algebra. And okay, so we have small x and z transform to big X, just as usual. And okay, this is not intended. Okay. And as we said, we want to take a z in the polar coordinate. So this is similar to when we do Laplace transform, we take the s to real part and imaginary part. And now we take z to the magnitude part and the angle part. So z equal to r to the r times e to the j omega. And we think about so what is this thing? And so we go back to the definition of z transform. So big X of r times e to the j omega is summation x, and r e to the j omega minus n. And then we can separate this into the r part and e to the j omega part. Then we see that we can write this as a summation x of n times r to the minus n and times e to the minus j omega and summation. And now you see that this is the Fourier transform of this curly bracket part, right? Because Fourier transform is just discrete and Fourier transform. It's just this on e to the minus j omega and times your function. So we see that big X of r e to the j omega is just Fourier transform of x of n times r to the minus n. Okay, that's what we say. So just like in Laplace transform. Okay, and so you see that for different r, you are just doing for every r. So back to this. So for every radius, you are basically doing a Fourier transform to a different function. So function times the different exponential decay rate r to the minus n. Okay. And as we say, so for r equal to 1, then this r to the minus n doesn't do anything. And that means that's on the unit circle, absolute value z equal to 1, then you are, so for r equal to 1, you are, this thing just go back to the Fourier transform your function. Okay? So x of z at z equal to e to the j omega is Fourier transform. And you see that coincides with our notation before, is big X of e to the j omega. So when we write this in chapter 5, we are already thinking about we want to write big X of z. Okay, and as we say, that's on the unit circle. And let's see the picture once again. This is a picture with these things. So think about z transform, and you think about z in radius r and angle omega. And as we say, the transform on this unit circle is the same as the Fourier transform of your signal, where the omega is angle omega here. Okay, any questions so far? If not, let's go into an example. Okay, so our favorite example is exponential decay cutoff at t equal to 0 or n equal to 0. Okay, so x of n equal to a to the n u of n. But now we are doing the transform, so this a can actually be exponential growing. So even if you are having a very unstable function, if you pick your z carefully, you can still converge, as we will see. But okay, so let's brute force through the algebra first. So big X of z, then just plug in a formula equals summation n minus infinity to plus infinity a to the n un, this is ux(n), then times z to the minus n. And then we do something, so u of n just cut off your summation from n to 0. And then you see you have a to n, z to the minus n. So this is just a geometric series. This is a times z to the minus 1 to the n, right? You just export the powers you multiply together. Okay. So this is a geometric series of a z to the minus 1. Okay. And then first we want to see the convergence. So you are summing a geometric series, you want to converge, then you want your coefficient here to have absolute value less than 1. So az to the minus 1 should less than 1. And you move things around, that means your absolute value of z should be bigger than absolute value of a. And that makes sense, right? So if a has like a bigger than 1 absolute value, then your z. So if your a is exponential growing, you want your z to be exponential decaying faster than a. So you actually get a convergent series. Okay. And okay, so if you are converging, then you just apply your formula, your summation, your geometric series is 1 over 1 minus r, right? And okay, so it's 1 over 1 minus a minus 1, a times z minus 1, sorry. 1 over 1 minus a times z minus 1. And okay, so yeah, so this is the function we are going to see all the time in this class because it corresponds to this exponential decaying function, and this is basically the basis of the rational function we are going to take, and all the inverse Laplace transform, partial fraction expansion, etc. You are going to do this. And well, it's not as nice as the Laplace transform one, unfortunately. Laplace transform, we just have 1 over s plus a, right? It's not as clean, it's 1 over 1 minus a z minus 1. Okay, so it's a little more ugly, but it's still a rational function, and that's nice. So even though we take the like exponentiating of the s, right? So we say like z equal to e to the s, and then we do the transform of this exponential decay function. It still gave you as a rational function of z. As you see here, that if you multiply the upper side and the lower side both by z, then you get z over z minus a. Okay, and then we have ROC as we want. ROC is absolute value of z bigger than absolute value of a. Okay, and let's see picture first. So this is the thing. So this is a picture we had before, and it's a picture for this is the transform. So you have pole at a. Here we have the absolute value of a less than 1. So the pole is inside this unit circle, and your ROC is for every absolute value z bigger than absolute value a. So everything outside of this ring is your ROC. And also you have a 0, just because you have a 0 at z equals 0 here for this z. Okay, so you have a 0 at here. So this is your pole 0 plot, and ROC for very basic a to the n u of n. And obviously if so this is for a between 0 and 1, and if a is bigger than 1, then your pole will be outside this unit circle and your ROC is still outside, then your ROC will not include this unit circle, and your Fourier transform doesn't converge, etc. Right? And also you can have a equal to 1, then your ROC is exactly on the unit circle and it's a bit weird, etc. Yeah, as we see, this is a rational function. Okay, so any question about this? The transform, this first example, which will be a basis of a lot of calculation we're going to do. So I guess take some time to get a little familiar with this. Again, x of z equal to 1 over 1 minus a times z to the minus 1. Okay, this is probably the base form for it, and it's a rational function. Okay, and yeah, now if you remember what we do in Laplace transform, you can probably guess the next example. So next example, we are going to get the Laplace transform of the same form but a different RC. Okay, so it is exponential decay to the other side. Okay, so minus a to the n u of minus n minus 1. Okay, so it's like so if for a bigger than 0, it's like this exponential decay here. And it's from, so we have u of minus n minus 1, and we want this to be bigger than 0. And the moving around, it means that your n is less than equal to minus 1. So we are taking n from minus 1, minus 2, minus 3 to minus infinity. Okay? And yeah, then is this thing, and let's see how this Laplace transform goes. Is it what we expect? So x of z, big X of z is summation n and your x, so your minus sign outside, and an is u and z to the minus n. And as we said, this u will take your n from minus infinity to minus 1. And then you are left with a to n z minus n. Okay. And let's see what we do. Oh, okay, so we do a change of variable. So we change n to minus n, so make things a little nicer. So summation is minus n, so from 1 to infinity. And all those n become minus n, so a of minus n, z minus n. Okay. And so summation from 1 is a little annoying, so we add back to the n equal to 0 term. And so that should give you a minus, when n equal to 0 is 1, so it should give you a minus 1, so we'll add an extra 1 here. So 1 minus, so n starting from 0. Okay. Let's do intensify. Okay, so because we do n from 0, so we get an extra 1 here. Okay, so this is n from 1 to n from 0. Okay. And now we want to, once again we got this geometric series, and we want to see when does it converge. And it converge when absolute value of this thing is less than 1. And then you move around, and you see the absolute value of z should be less than absolute value of a. And it's a different direction than before. Before is absolute value of z should be bigger than absolute value of a. And yeah, then you do geometric series 1 over this. 1 minus this 1 over 1 minus r. And then you equating that together, then you get this a minus 1a on the upper side, then you divide everything by a minus 1z, and you divide everything by a minus 1z, I believe. Actually negative. But anyway, I think you can do the clean up here, and you see that you get the same form, 1 over 1 minus yeah, so you actually get those things. You equate the lower part, and you get a minus a to the minus 1z, and you divide both the upper side and both the lower side with minus a minus 1z, then you get this thing. And yeah, so you see that this is the same as before, is z over z minus a, but now you have the ROC on the other side. ROC is, can I do eraser on this thing? No. Okay. Yeah, then ROC is the other side, absolute value z less than absolute value a. Okay. And we didn't include a figure, but you can kind of imagine from here. So it's the same thing, but the ROC is inside here. Okay. Okay. So question from those two examples is x of z equal to z over z minus a, and you can have ROC outside and inside, and they correspond to exponential function on the positive side and the exponential function on the negative side. Okay. And next, see another example of we do linear combination. And as you expected, the z transform is also linear. So you do this linear combination of two exponential function, you get the corresponding linear combination of your big Z. But let's first do this in the stupid way. So you just plug in the formula. So you plug in big Z equal to the summation, this function, and Z to the minus n. Then you see that this form is very linear. So it's really just a linear combination of those two transforms. So 7 and this 1 over 3 Z minus n, 1 over 2 Z minus 1 over 2 n Z minus n. And it's the summation 1 over 3 Z minus 1 to n, 1 over 2 Z minus 1 to n. Okay? And then you can do those two things separately, geometric series. Then you get this familiar form. So 7 over y minus 1 over 3 Z minus 1 minus 6 over y minus 1 over 2 Z minus 1. And then you can just brute force your algebra and so combine those two terms and get still a rational function of z, or it's more like a rational function of z minus 1. But we are plotting on z plane and z minus 1 plane, so you want to multiply all the z minus 1 and become a rational function of z to see where are your 0 and poles. So you see that there are two zeros and two poles. Pole is minus 3, 1 over 3, a pole is 1 over 2, and 0 is 0, and 0 is 3 over 2. And okay, but there is something a little careful we need to be a little careful about is the RLC, right? So we kind of jumped through one step here. So when we take a geometric series, we need to make sure that our z is taking a value where those two geometric series both converge. And so that's basically the RLC of z bigger than 1 over 3 and z bigger than 1 over 2. So the intersection of both of them, so we should take the most strict one, so that's z bigger than 1 over 2. Okay, so maybe it's easier to see here. Okay, so one of them has RLC bigger than 1 over 3, one of them RLC bigger than 1 over 2. So when we take both of them, you take the outer RLC as bigger than 1 over 2. And you see the pole 0 plot, you have two poles and two zeros. Okay? And yeah, somehow when you add them together, you get HR 0. Just because in Z transform have this founding form of Z minus 1. And that's why. Guess. I guess in the Laplace transform can also get HR 0. Yeah, Laplace transform can also get HR 0. But anyway, so you see that you add them together, you get HR 0, but the poles are same number of poles here. Yeah. And yeah. As we see that this is linear, so you see this calculation is very linear, so you can just do or you can also just do a Z transform both of them and add them together and take the intersection of the RLC, just like before. Okay? Take the intersection of RLC and also as you can imagine, if there is pole cancellation and you want to extend the RLC, etc. Okay. So yeah, those are the pole 0 plot. So first Z transform first term, Z transform the second term, and Z transform the linear combination. You'll see both poles and the poles didn't cancel, and then you take the RLC, which is the intersection, which is the outer one, and you get HR 0. Any question? Okay, if there is no question, then let's see the next one. So next one, basically the same thing, although we get a little more complex number here. So we have the exponential decay and times sine. And you should be very familiar with this sign now. When you see sine, you can just break them into complex exponential by our inverse order equation relation. And yeah. So sine is the difference between exponential with 1 over 2j. Okay? and then this exponential. So this e to the j pi over 4n is also is the e to the j pi 4 to the nth power. So you can combine with this 1 over 3 to become a complex number to nth power, and the other negative exponential is also something to the nth power with a negative sign on your exponent here. Okay. And yeah, so then if you write it in this form, then it's just like this question. So you are just having two of those exponential function as a linear combination. So you do z transform, then you basically just plug in formula. So it's 1 over 2j minus 1 over 2j, and z transform this is 1 over 1 minus a, z minus 1, 1 over 1 minus a, z minus 1, with a1 being 1 over 3 e to the j pi over 4, and a2 is 1 over 3 e to the minus j pi over 4. Okay? So just like before. And yeah, so this is your z transform, and we're just copying this here. And if you want to write everything together as a rational function, then you multiply all this. The calculation might be a bit ugly, but we skip all the calculation, and the result is this. So this is in the rational form. Yeah, we believe that we do the calculation right. So 1 over 3 over root 2z, and you can see the two roots here, so they should be correct. So the root is 1 over 3 e to the j pi over 4, and 1 over 3 e to the minus j pi over 4. And for convergence, then convergence is just as before. You want to have absolute value of z bigger than absolute value of a. And the absolute value of a here are both 1 over 3, right? Because you get this extra exponential function, you take absolute value, it doesn't do anything. This imaginary exponential doesn't do anything. And yeah, so both of them ask you to have z bigger than 1 over 3. So the RC is just z bigger than 1 over 3. And when you do the pole-zero plot, you see you have those two pi over 4 angle, plus pi over 4, negative pi over 4 angle, and those two poles with radius 1 over 3, and 0 is 0 because from this z. Okay, so this is a pole-zero plot, and as we say, RC is bigger than 1 over 3. So all the outer part. Okay. Question from this example. Yeah, so this is another example of a linear combination, and once again we see that we can deal with sine or cosine by breaking them into complex exponential. Okay, and we are super fast. Maybe we'll stop early today. And if there's no question about those example of the transform, then let's go to the ROC of the transform. Okay, and yeah, ROC of the transform, as we say, is very similar to ROC of Laplace transform, except now ROC of Laplace transform are strips, but ROC of transform, Z transform are rings, because you are basically taking exponential in exponential in S, these are e to the S, so those straight lines are now circles. And yeah, as we say, RC consists of the x of z consists of the z rings in z plane, and is centered around origin. And just from the derivation we had before, the RC consists of the value of z, and so we separate z equal to the radial part r and e to j omega, and we think at a fixed r, this so at some fixed r, the z transform is just a Fourier transform of xn times r to the minus n. Okay. And once again, we think Fourier transform either converges for every omega or doesn't converge for every omega. So each ring just converge together or not converge together. Then there is something that we say that's very tricky for Laplace transform. That's we are equating this XR to a minus n. We equating it being convergent with it being absolutely summable. Okay, so we are also thinking that the LC are just a set of xn such that xn times r to a minus n is absolutely summable. So summation from minus infinity to plus infinity absolutely of xn times r to a minus n is a constant value. So if your R give you this condition, then we think you are in RC. And if it's not, then we are thinking you are not in RC. And here, once again, you should have some fun text where you should check this carefully in HOMA's book. I guess the good thing I want to say here is that this is a little better compared to the continuous case, right? Because the continuous case, we were complaining that absolutely integrable is just one of the three Dirichlet conditions. Remember when we take the discrete Fourier transform, we don't need three Dirichlet conditions because you are not discrete function. You cannot have a lot of maximum and minimum, right? You cannot have those infinite, very high frequency oscillations. Okay. And you cannot have discontinuities because you are discrete anyway, right? So if it's absolutely summable, then its Fourier transform will converge. And otherwise, if it's not absolutely summable, it's very easy to see that it's not converge. So now this sentence is actually quite rigorous, even without too much assumption or seeing a book. Okay? Because X over N is discrete, and so this is quite well behaved. Okay? But anyway, this is what we remember. RC are those rings where X over N r to a minus N is absolutely summable. Okay, and so we're rings. We're jumping ahead of ourselves a little bit, but you can probably guess this. Anyway, so let's mimic what we had before. So property 2, RC does not contain any poles. Okay, and just like in Laplace transform, is because when you are at the poles, then your Laplace transform goes to infinity, and obviously it does not converge. And then property 3, if you are finite duration, then your RC is entire S-plane. So up until this part is same as the Laplace transform, but then we have caveat. So it's actually not entire S-plane, entire Z-plane, because you might not include Z at 0 or Z at infinity. Okay, so this is a bit tricky. So it's entire plane is at 2 points, Z at 0 or Z at infinity. Okay, and let's see the first part. Okay, so when you have finite Z, then things are easier. Okay. So finite duration, sequence. So let's say your sequence is from your small n from some big n1 to small n from big n2. So finite duration from n1 to n2, and then you can write your Z transform by just brute force. So you sum your xn times Z to a minus n, and obviously you only need to sum from n1 to n2. Because xn only have value from n1 to n2. Okay, so this is interesting. And so now you see that these obviously converge if your Z is not finite value, right? Because you are just summing over finite 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 number of terms with some finite value, right? So it is summing from n2 minus n1 plus 1 terms, and all of them have some finite value. So obviously you have any finite z, this will converge. But this z to the minus n can, well, z to the minus n can diverge at two value. It can diverge at plus infinity or 0. Right? So the infinity or 0, it can be bad. So if your z is positive, this z to the minus n is like 1 over z to some power. And you see this thing will diverge when z equals 0, right? So 1 over 0 is infinity. And if you are on the positive side, then this z to the minus, so if n is positive, if n is negative, then z to the minus n is like z to some power. And z to some power will diverge when z goes to infinity. Okay. So this is why you might not include infinity or 0. And so like it's a base case, so we want to analyze this in cases. So let's say your n1 is negative, n2 is positive, so you are crossing between 0, and so you both have the positive n term and the negative n terms, right? So you both have those like z term and 1 over z term. Then one of them divergent infinity, one of them divergent 0. Then you see that both z equal to 0 and z equal to infinity should not in your RC, because z equal to 0 doesn't converge with 1 over z, and z equal to infinity doesn't converge with z. And okay, but sometimes you can still include one of them. So let's say, actually you can include both of them. So okay, but let's see what case they can be included. So let's say your n1 is positive or 0, so you are starting at here, okay. Then all the terms, so n1 is positive or 0, then you don't have negative n terms. So all the terms are like z and so you don't have those 1 over z term and I got the other direction. So n1 is positive or 0, then n is positive, so you only have those 1 over z terms, so you don't have those z terms. And so at z equal to infinity, they will converge, right? Because you don't have those kind of terms. Those kind of terms converge at z infinity. Okay. And the other side, so your upper bound is 0 or negative, then every n is 0 or negative, and so you only have this kind of turn and you don't have this 1 over z kind of turn, and so you flip the logic all around, so your ROC should include z equal to 0. Okay. This is a lot of time to analyzing something not too interesting. But yeah. But anyway, so although there are only 2 points, you need to be careful about the z equal to 0 and z equal to infinity. So I think when you are doing homework or exams, you should include where there are pole 0 at infinity or 0, and your ROC you also need to just think about where your ROC includes 0 or infinity. And okay, so let's see an example. So we kind of see that you include only infinity or 0, but actually there is a very special function that can include both infinity and 0. And it's our unit impulse, because unit impulse delta of n, it doesn't have z or 1 over z, it just have a constant. So if you are delta function, delta of n, remember it's just 1 at n equal to 0. And okay, so you do a z transform. So summation from minus infinity to plus infinity, delta of n, z minus n. Then you see that this pick all the n equal to 0 terms, so we just get 1 here. Okay. So Z transform is 1 and 1 converged everywhere, including Z equal to 0 and Z equal to infinity. And obviously you times some constant here, you get some constant here, it's still converged. Converged everywhere, including 0 and infinity. And it's like an intersection of those two cases. So we say n1 is 0 or positive, n2 is 0 or negative. So if both of the n1 and n2 are 0, then you both include the infinity and the 0. Okay, so yeah, so that's the case where you include both infinity and the 0, because n1 and n2 are both 0. And okay, on the other hand, if you shift this a little bit, so you think about delta minus 1, that's when basically you pick out so it's time delayed, so it's a spike at n equal to 1. And for this thing, so n equal to 1, so you get z to the minus 1. Okay. And as we said, and yeah, as we said, z to the minus 1, you will diverge z equals 0. So it has a point z equals 0, so the RC doesn't include the RC doesn't include z equals 0. Okay. And but this is converging at z equals infinity, because at z infinity this is 0. And yeah, so RC is everything except z equals to 0. Okay. And on the other hand, if you consider the advanced impulse, so delta n plus 1, which pick out n equals to minus 1, then you got z. And this is finite everywhere except at so this is also finite at 0, but when z equals to infinity, it diverges. Okay, so the RC is everywhere except the point infinity. Okay. Any question? If not, then I think let's stop for now, and we'll start 10 minutes later, and yeah, and we'll finish the properties, and maybe we'll go a little bit into inverse transform. Okay, yeah, so let's take a 10 minutes break. I think we are. Okay, let's get back. Any questions so far? I think maybe, yeah. Let's see, we're probably going to finish early today. Okay, and yeah, so following the Laplace transform. Wait, whoa, okay. Following the Laplace transform. Following the Laplace transform trick. So we have that for this finite duration function, its ROC is entire plane, except z equals 0 or z infinity. And then we have that for the wait, sorry, where are we? Okay, here. The next one we go to the right-sided sequence, and just like before, so right sequence is like this. We start from some n1, and then its ROC it should be, so for the Laplace transform ROC should be right-sided, and for the Z transform it means the ROC should be like an outer ring, go to infinity. So by in a more algebraic way, we say that if some radius in the ROC, then every finite z that's bigger radius is also in ROC. But here, once again, we have this weird thing that we only say finite value. So actually, the infinity point might not be ROC. Although every finite value that's bigger, it might be ROC, the infinity might not be ROC. Okay, so let's get a feel with the picture. So we say we have a right-sided function starting from n, so we have a bigger picture here. So right-sided function starting from n, and is something goes to infinity. And we are, and remember the first property we say that something is ROC if this xn times r to the n minus 1 is absolutely summable. And so you have some r0 times this thing is decaying with some rate is absolutely summable. So you think r0, then you go to some r1 that's bigger, and so r1 is bigger than r0, then it's going to decay faster, right? And then it should be absolutely summable, although it might have some higher ratio at the start. But here we don't run through the algebra carefully because we're seeing it in the chapter 9. But you can think about if you have some decay and make it absolutely summable, then you have a higher decay, it should still be absolutely summable. Although it might be timing some constant because the starting point might be higher. Okay, and so that's absolutely summable, but as we said, if your z go to infinity, it might become not absolutely summable anymore. That's because at the starting point, so you think you get a bigger and bigger r, then the starting point here can get higher and higher if your n1 is less than 0, right? If your n1 is less than 0, then yeah, so you see at 0, those r to n are all starting at 1. But for the negative part, when your r get bigger and bigger, your starting point get higher and higher. And as r go to infinity, it might diverge. Okay, so this head here might diverge if your r go to infinity. And we see it in algebraic, the divergent infinity, you can see it here. So if your n1 is, okay, so we're seeing it a little more careful. So your n1 is negative, right? So you start with some negative x of n, then you are getting terms with basically z to the minus n with negative n, so you get like a positive power of z, so like a z and a z squared, etc. And once again, as we said in a previous property, the positive power of z can diverge when z goes to infinity. So yeah, so property 4, your ROC is like a ring that goes to radius infinity, but it might not include the actual infinity. For the actual infinity, for the actual infinity, if you want to it be ROC, then it depends. So there is a one-way relation. So if n1 is positive or actually it says like if only if here. Okay, so if your n1 is 0, if your n1 is 0 or positive, then obviously you don't include any of those positive power of z, then infinity will be inside. And if your n1 is negative, then it's a little weird. But yeah, I think if n1 is negative, then infinity should not be inside, because you probably cannot get the cancellation. Okay, yeah. Then you get those positive power of z, and you should not have infinity as your in your RC. Okay, and but one interesting thing here is if xn over n, if you think about it as an impulse response, then if it's causal, then it means that you are starting from n equals to 0, right? So if you are causal, then you only get those positive n terms, and that means that infinity is in your RC. Okay, so we should say right. So this. So if you are causal sequence, then infinity is in your RC. Okay. Okay. And here is a little spoiler. So as we said, the right-sided RC should look at this thing that push to R infinity, but might not actually include R infinity. And then there will be a left-sided, which is just reverse, and there will be two-sided, which should be a ring. Okay. So yeah, as we say, a left-sided sequence is some x over n that stop at some n2 here. Okay, n2. I write this 2 a little bit better. Okay, so you sum to some n2, and you should push your z to around 0. So if some R0 is in your RC, then between 0 and R0 is all in your RC, so we'll push inside. But just like infinity might not actually be RC, here 0 might not actually be RC. That's because if your n2 is positive, then you include term like 1 over z, and 1 over z actually diverge at 0. Okay, so only if your n2 is less or equal to 0, then your RC will include 0. Okay, so it's just a reverse of this situation, left and right. Okay, and then finally the two-sided function. So we don't really have a bound on left or right, but for two-sided function, we can do the analysis just like in chapter 9. So two-sided function, we can break it into a left-sided function and a right-sided function. Right? Let's draw this a little bit. So we say we can cut off a two-sided function at any point. Oh, here. Yeah. So two-sided function. So no discrete terms or whatever. So two-sided function, you can just cut off at some point, and so you have a right-sided function and a left-sided function. Right? Okay. And as we said, so it's easier to say with a picture. Say this in a picture. So two-sided function is like a summation of right-sided function and left-sided function. And so ROC should be like an intersection of those two. So if you have an intersection, then it should become ring. So there is one ring, so you cannot have double ring, etc. Just like in Laplace transform, you only have one strip. And then if there is no overlap, then you have no ROC. And also you can push all the way to 0 or push all the way to infinity if those two things are big enough. Okay. And yeah, I think the words are just saying this. Your two-sided function, you can think of it as the left side plus the right side. And you think about the ROC being the intersection of those two ROC. And okay, then let's see some examples. So first we have a finite duration signal. X of n is a to n just like usual, but it's stopping at some finite duration. So n from 0 to n minus 1. Okay. And for a bigger than 0. A bigger than 0, I think it really doesn't matter, but make things a little simpler. Anyway, so big X of z, then we plug in the formula, so summation 0 to n minus 1, an z to n minus n. Okay, so the 0 to n minus 1 is just this range. And once again, this is a geometric series, although it's a finite duration geometric series. And but you plug in a formula, so 1 minus r and 1 minus r to the n, I believe. Yeah. And well, we also have a0, so the first term is just 1, so we have 1. Okay? Anyway, this is a geometric series formula. And then you turn this back to a rational function of z because we want to put point 0 in terms of z. So you multiply all the z minus 1, and let's see this a little carefully. So there is the n power of z minus 1. So you multiply both upper and the lower with z to the n. So you got z to the n here, and then this one can cancel out, so you get a. So you are left with a to the n. Okay, and so z to the n, z to the n. Wait, oh, okay. Yeah, so the upper part z to the n and lower part z to the n. And the upper part z to the n multiplying with this thing get you this. And lower part you have z to the n. But you also get, you should actually also get an HRZ minus 1 here. And so that's like you multiply upper part and lower part with z again. So the lower part z gets this, turn this into z minus a, and leftover z cancel with z to the n, so you get z to the n minus 1. Okay. So anyway, as a rational function of z, look at this. And if we want to really express this in rational polynomial, we should break this a little more, but because this is still not roots, right? So it's like z to n minus a to n. You can break it into n roots of z, but it's easier to see those roots in this form, so let's keep it as this. And okay, so what are the actual roots? So roots of this z to the n minus a to the n is, so you solve this equation, you see that z to the n equal to a to the n, and then you take n complex root of a to the n, and you see that you get those. So you take nth root of a to n, so that's a, but it's complex, so you are having like n equally spaced out value around the circle. So it's a times e to the j 2 pi k over n, okay, with k from 0 to n minus 1. So it's these points, okay. So it's a and e to the j 2 pi over n, e to the j 2 pi 2 over n, etc. So you have those n roots with on this radius and a ring. So let's see a bigger picture. So you have n roots here, and but actually one of them will cancel with this 0 as z minus a, because one of them is a. So for k equals 0 is just a. So you have roots at the upper part at a and the roots at the lower part at a. So basically you have a term of z minus a cancel with z minus a. Okay, so you can actually divide all this a little more, and you should get this thing. If you remember from middle school, I believe. So you divide all this, it should become a polynomial of the n minus 1 times the n minus 2a plus the n minus 2, the n minus 3a squared, etc. all the way to a to n minus 1. And the thing about roots of this polynomial is this thing, is those n minus 1 roots here. Okay? So that's a little refresh on polynomial analysis. But anyway, there are n minus 1 zeros on the later part, and obviously there are n minus 1 roots at z equal to 0, just from this 1 over z to the n minus 1. So yeah, so there is n minus 1 order 0 at z0, and there are n minus 1 different zeros. So there is n minus 1 order pole at 0, and there is n minus 1 zeros around this circle. That's the pole and 0 here. And then okay, so we spent a lot of time saying about the pole and 0, but we want to say ROC. And as we say, it's finite duration, so ROC should include everything except possibly not including 0 or infinity. Okay, and well, from this thing or from this form, we see that as z equals to infinity, they all converge because this is a polynomial with power, with the numerator power is equal to the denominator. So, so the RC equals everything on the plane, and except 0 is obviously not in RC because 0 you have a pole, and at infinity it is included, and excuse me, and that's consistent with our discussion because we see that it's n0 and n1, so n0, so n1 and n2, so n1 is 0 and n2 is n minus 1. So because n1 is cut off at 0, so it's greater or equal to 0, so infinity is in your RC. And you can also check from here that infinity should be your RC. Take a z to infinity, that's like is 1. Okay? And 0 is not in your RC because you have those positive terms. Yeah, because of those positive terms, so 0 is not in your RC. Okay. So this is an example of finite duration function. It has a quite interesting pole 0 plot. It has a lot of zeros. Okay. And ROC is everywhere except this pole is 0. Okay. Then let's see another familiar example. So our double-sided exponential function xn equal to b to the, okay, and the remainder you can look like either this or this. So if b is between 0 and 1, then it's a double-sided exponential decay. If your big E is bigger than 1, then it's pretty bad. It's a double-sided exponential growth. It looks very unstable. But okay, anyway, this is a two-sided signal. And as we said, we can cut this two-sided signal into a right-sided sequence, right-sided signal and a left-sided signal, and think about the RC of each of them. So the cutoff length is n equal to 0, as usual, but okay, so we cut off it by its discrete time, so the cut is a little weird. So we are cut between the n equals 0 and n equals minus 1. So for n greater or equal to 0, we cut it into this p to n u of n. And for n less or equal to -1, is this p of minus n u of n minus 1, u of minus n minus 1. And so the first one we know is the transform very nicely because we've done it in the first example. It's 1/1 minus b z minus 1, and our c is z bigger than b. And for the second one, we compare it to this minus a to the n, u of minus n minus 1. So you see this is still very similar. You just get extra negative sign in our example 10.2. And a negative sign here, and also a difference between here, right? So we had a to n, but here we have b to the minus n. So actually we should take a equal to 1/b. So you get minus 1, and this 1/1 minus b to the minus 1, and z to the minus 1. Okay. You have a minus 1 because you have an extra negative sign here. And then the ROC is the inside thing, but here a is actually 1/b. So your ROC is absolute value of z less than this absolute value of 1/b. Here b we just take a real value, so it's just 1/b. Okay, so right sided is this thing and left sided is this thing. And then we think about their intersection, so it's easier to see, just see the picture. Okay, so if b is bigger than 1, then the ROC of bigger than b look like this, and ROC of less than 1/b look like this, then you see there is no intersection. And that confirms with our expectation that this really weird function, it doesn't have a z transform anywhere. Whatever z you take, it doesn't converge. Okay, and you can see from the left side and right side analysis that they don't have overlapping ROC, so they cannot converge with the same time. So yeah, so there is no ROC. So for the z transform of this thing, they just doesn't converge anywhere. But if we want to have a better example, so now we change b to be between 0 and 1, then you see that the right sided ROC look like this, and left sided ROC look like this. Then you see you have a ROC between b and 1/b. Okay, and so if b is less than 1, you actually have a ROC. And then your algebraic part of your z transform is you adding together those two terms. Then you add together like this, and you can equate the lower part and get a rational expression like this. And so you see a rational expression, so you see you have a 0 at the z equals 0, and 2 poles at b and b minus 1. Okay, so pole 0 plot look like this. Okay, any question? Okay, if not, then let's finish the last 3 properties. Okay, property 7. Property 7 is just like property 7 before. So if your z transform is rational, then it's a very nice function, and your ROC are bounded by poles or extend to infinity. Okay, so I guess the proof of this is probably you just do the inverse z transform as before, and you'll see that you have those kind of ROC. Because the rational function, you can always do the inverse z transform. And okay, so it's bounded by poles. There is nothing too weird. And also, then property 8 and 9, for it's derived just from the combination of the previous property. But in chapter 9, we only have one property, but here it's longer, so we break it into 2. So it says that if you're rational and also your signal is right-sided, then your ROC should take the almost ROC, right? And do we have a picture? Maybe let's use this. So say like your function like this, and it's rational, and there are 2 poles. And if the right-sided, then you should have the almost ROC, the one outside your pole and possibly push to infinity. But now once again we have the caveat that we had before. So the ROC is the outside most one, but infinity might not be in your ROC because you might have some negative you might have some negative n terms z to the positive n because minus n is negative, so minus n is positive. Yeah. But anyway, so infinity might not be your ROC. So infinity is your ROC only when you are only summing over positive n. Okay. And that's when that means your xn is causal. Okay. So when your xn is 0 for negative n, so only summing over n from 0 to infinity. Okay. So if your xn is causal, then you also include you also include the infinity point. Okay. This is if only if actually. Yeah. I think we can say if and only if. Okay. If and similarly, so that's for the right-sided, and for the left-sided is similar. So if you are rational and you are left-sided, then you should take the inner part. Sorry, too much. So if you are left-sided, so you should look at the innermost pole and take the innermost part. And yeah. Oh, actually there is a little more. So it's the innermost and non-zero pole. Okay. Yeah. Highlight. So you should take the innermost non-zero pole, so the 0 pole doesn't count. Okay. Yeah. And yeah. So you push towards 0 from the innermost non-zero pole. And also, if you want to include z equals 0, then all those terms should not have positive n. And and that means your x of n should be anti-causal. So for n bigger than 0, your x of n should all be 0. Okay. If and only if in that case, your ROC will include z equals 0. Okay. So that's all the property. Any question? If not, then okay. I think then let's finish this example and let's have already finished. Okay. And yeah, we basically do this example already. So let's think about this function. Okay, so z equals to 1 over 1 minus 1 over 3 z minus 1 times 1 over 2 z minus 1. Okay. And okay. And it has pole 0 plot. We didn't multiply but you can imagine, right? So from here you can just read it from here. They should have a pole at 1 over 3 and a pole at 2. Because if z equal to 1 over 3, then this is 1, and z equal to 2, this is 1, and you got 0, 0. Okay. So you should have a pole at 1 over 3 and a pole at 2. And also think about your multiple z through everything, you should get a 2z on the upper part, so you have a 2, 0 at 0. Okay. But anyway, there are zeros, but the poles are at 1 over 3 and 2, and that cut the radius of this z-plane into 3 parts. So between 0 and 1 over 3, and between 1 over 3 and 2, and between 2 and infinity. So there are those 3 possible ROC for your x of z. And as we said, the almost one is right-sided here, and the in-between one is two-sided. Okay, so let's highlight this. So the almost one is right-sided, and the innermost one is left-sided, and if you are in between one, your function is two-sided. Okay, and you can imagine that, although we haven't talked about that, which we will do in next class, you can imagine you do partial fraction expansion of those, and between choosing different RC, you will get the different inverse of the partial fractions. You will get partial fraction back to example 10.1 or example 10.2. Let's see. We are still a little early, but I don't think we should. Little saying we didn't say here, and also include a unit circle. Okay. Something we didn't say, but you can probably guess from the Laplace transform is also the next one is the only one that you also include a unit circle, and obviously when you include all these unit circle, that's when your Fourier transform converge. Because remember, Fourier transform in the Z plane correspond to this unit circle. So you also include a unit circle if only if your Fourier transform converge. And that also means your signal is absolutely summable, and that means your system is stable if your signal is actually impulse response. Okay, so we got 20 more minutes, but I don't think we can finish inverse Z transform. Okay, let's get a very quick view about the inverse Z transform. So inverse Z transform, there's going to be a little more method. So the first method is like before, we are going to do contour integral. So maybe let's jump to page 5. Okay, jump back to here. So remember when we do the contour integral for inverse Laplace transform, we say we want to do some contour inside this ROC from like negative infinity omega to positive infinity omega, like a straight line. And if you convert that to a Z transform, remember a straight line here is a circle here, then the inverse Z transform is going to be a contour around some circle inside your RC. Okay, so for here you can, and remember your RC has no pole inside, and your contour can really be any shape. If you stretch your contour around some place with no poles, will get the same integral. But anyway, your contour integral will be like a circle inside your ROC, and that's an inverse Z transform. And in algebraic it's like this, but it actually has something different. You have the Z to the minus 1. So compared to before, you have this XOT to the minus ST. But in the Z transform, in a Z transform, you get this weird Z to the minus 1. That's just what the math told you. So in the Laplace transform, you have the e to the minus t, e to the plus st, very symmetric, but here you have z to the minus n, but actually z to the minus 1. That's just what the math give you. And the method 2 is also similar to before. Is you do partial fraction expansion. And as we see that we are basically want to map back to our exponential decay in either positive side or negative side. And those are all from those 1 over 1 minus a 1 over a z minus 1. Sorry, actually a times z to the minus 1. So we want this kind of form, right? So we want to actually not express our x of z in the roots of z. We want to express it in roots of z minus 1. So we want to rewrite our polynomial in terms we want to rewrite our big X of z into those polynomial of z minus 1. Then we do partial fraction expansion. And if you do that, then you can break it into, okay, so the lower part you get into those z minus 1, so it's like root of z minus 1 in this kind of form. And you do partial fraction expansion, and then you get into those kind of partial fraction, and you can do inversely transform by looking at whether your ROC is on the outer ring or the inner ring, etc. Okay, so that's a very quick review. And then, okay, so those are the two methods we had in Laplace transform. But we are going to see next Tuesday that we actually have more method. Okay, so maybe here. So in terms of inverse Z transform, we are going to see that because Z transform has some extra properties. So basically because you see that let's see. Okay. There's some hacking you can do to do inverse Z transform. That's because remember your x over z is this xn times z to the minus n. So this is actually just a power series of z to the minus n. So if you can just write your x over z in this form, then you can just read your x over n from here. Okay. So a very quick example, if your x over z is just this, so it's a power series of z with positive power and negative power, then you can just read your x over n to like a 4, 2, 3, 0. 4 at n equal to minus 2, and 2 at n equal to 0, 3 at n equal to 1, and 0 otherwise. Okay? So we just try to fit your x over z into this form. And here we are just writing it in this form. And if x over z is not in this form, then there are ways to turn it into things like this form. Like here, one of them you can do division, and or you can do Taylor series expansion if you remember from your calculus. Okay, so we jump a lot, but we'll do this carefully on next Tuesday. But just going to show you a little bit about inverse Z transform, and yeah. So I think that's it today. We'll finish early. And any question? Otherwise, let's just stop here. Okay, let's stop for now. Okay.